I'm going to talk today about learning to reason. It's a joint work with Amnon Shashua and a team of very talented people at AAI. The mission is to achieve scientist-level AI. So if we look at today AI, there are two axes that we can think of. One is a breadth of tasks, and with a revolution of large language models, tasks became much more wider in the scope of the problems that they can tackle. And the idea was to reach artificial general intelligence, or AGI. The same model can solve many, many tasks. But there is another axis, which is a task difficulty. And today, AI systems are very capable, but they are still far from being expert. And if we think about the real potential of AI, it will come from getting an expert-level AI. It doesn't need to be very general. We don't need our AI to be able to run very fast in order to be an expert in mathematics or in computer vision or in any other narrow domain. So it can be a narrow AI, but it must be much more capable than today in terms of the difficulty of the tasks that we are aiming to solve. And this is what I'm going to talk about, how to reach expert-level artificial intelligence, one that can be a good scientist. So what is science? In a nutshell, science is converting observations to rules. So if you think about the modern way to think about science, or at least the mathematization of science, it is machine learning, it is classical PAC learning. There are observations, pairs, X and Y, and we are looking for a rule that explains the observation. This is what science is about, finding rules that explain observations. So X is an input, Y is an output, and we are looking for a rule H that maps from the input space to the output space. And the real effort is to come out with rules that generalize, meaning that they are not only good on the observations that we have already seen, but they can also generalize to new observations and can give us predictions about the future. So if we look at modern deep learning, how does it tackle the classical learning paradigm? So if we go back for a moment, we need to define how we represent the inputs, how we represent the output, what is the type of rules that we can allow to match between input to output, and how we find this rule. What is the algorithm that finds the rule? So in modern deep learning, the idea is that observations or inputs and outputs are tokenized, meaning that we switch everything to a language. We just want to describe everything that we can describe in Word can enter a large language model. So we take the inputs and describes them in a language, and then they are tokens in a language. The output is the same. As to the rule, the type of rule, the most commonly architecture is a transformer architecture. And the learning rule itself is stochastic gradient descent. So this is maybe in a nutshell everything that is going on in modern machine learning today. Now the question is, can deep learning do science? So can we take observations, describe them in language, run a transformer, and hope that it will find the underlying rule? So in order to tackle this question, let's start with a very, very simple example, long multiplication. So the goal is very simple. We describe an input. It's a sequence of digits describing a number A, and another sequence of digits describing the number B. And what is the output? The output is the digits that describe the product of A times B. And the question is, can modern machine learning learn this simple rule? So do this simple scientific work. The scientific work is to get many observations of, as input, pairs AB, and as output, the multiplication of A and B. And we want to learn the underlying rule in a manner that will generalize. So the bad news is that there is a strong negative results, that if we take transformers as our set of rules, train them by stochastic gradient descent, then they either memorize or fail. In any case, they do not generalize. So our scientific experiment failed, and modern deep learning cannot do science, even a simple scientific problem of learning to multiply two numbers, okay? So what is missing? The thing that is missing is reasoning. And to describe reasoning, we can think about Kahneman and Tversky system 1 versus system 2. What we did in the long multiplication example, we used system 1. We tried to directly map the two numbers to their multiplication. But this is not how we teach kids in school to do long multiplication. What we do is we show them step by step the algorithm of long multiplication. And there is a big difference between system 1 and system 2, which I will try to argue. So what is system 2? What is the other way to teach long multiplication is via chain of thought. The idea is that instead of mapping directly from x to y, we let x be v0, and then we infer v1 from v0. This is a reasoning step, and then comes another reasoning step, v2 from v1, etc., until the last step, vn, which is the answer. And all of this sequence is called chain of thought. Now, we prove that long multiplication, as our running example, is easy to learn with chain of thought learning. So if we show a transformer a sequence of v0, v1, which are the steps of long multiplication, then it will manage to learn the long multiplication algorithm, and when it will get new pairs of two numbers, it will know how to apply the algorithm and get the right answer. In contrast, as we showed before, end-to-end training of two numbers into their multiplication fails. So what we see is that chain of thought is significantly stronger than end-to-end. And the reason is that each individual step is much simpler than figuring out the entire thing. So this brings us to what is happening today in modern deep learning, the reasoning area, where we see large reasoning models that can do more and more and more reasoning tasks. But let's take one step back and ask the fundamental questions. What is learnable with chain of thought data? So what types of things can we learn if we show these v0, v1, v2 to a model? Can we learn everything with chain of thought? And how to learn from chain of thought data? So again, the chain of thought is a sequence of reasoning steps, and the question is how to learn the mapping from step to step. So the first approach is to apply supervised fine-tuning with teacher forcing. So we have a pre-trained model. Then we show the model as a context, we show the previous steps, so say v0 to vi, and it needs to maximize the probability of the next reasoning step. And what's important here is that we are using a technique which is called teacher forcing, meaning that when we ask it to come up with a probability of the next reasoning step, we show the ground truth or what the data already figured out the previous steps. Okay, sounds good. Does it work? So there are two reasons why supervised fine-tuning fail for reasoning tasks. One of them is lack of search, and the second one is distribution drift. So I will try to explain these two issues. The first one is lack of search. If you think what is reasoning, then the best way for computer scientists to explain reasoning is as a search. a search in the space of ideas. So we have a problem depicted here on the left. I don't know if you can read, but it's a simple mathematical question. It proves that there are no co-primes that satisfies a squared plus b squared equals 6c squares. There are no 3 co-prime numbers that satisfy this equality. Right? So it's a simple exercise in mathematics, and we need to apply reasoning in order to solve it, in order to prove if this lemma is correct or incorrect. The way a mathematician will tackle this problem, most people do not know how to solve it immediately, but they have an idea of several directions to tackle. So one direction is to try to prove that there is a strict inequality. If there is a strict inequality, then there cannot be equality. So we can try this and get one direction, and then we get it doesn't work. So this reasoning fails. What do? We need to backtrack. We need to start again. So let's try a different technique. The different technique is, let's take modulo of 2 sides, and if 2 sides are equal, then their modulo must be equal as well. So let's try this approach. So we try this approach, but then we have a parameter, modulo of what? So we can try 2, we can try 3. If we try 2, it fails again. If we try 3, it succeeds. So this is how an expert that tries to solve a difficult task tackles a problem. There are many steps with uncertainty about the solution. We need to try out some stuff, see if it works, understand that it doesn't, backtrack to the right place, and continue from there. So this is what we call thought process. All of this back and forth of trying different things and going back and try again. But what is our data? Our data is just a thought outcome. It's just a path that finally worked. We don't see all the thought process, but only the thought outcome as chain of thought data. So there is a gap between the data that we have and the data complete data that explains the entire process. So this is one issue of lack of search. Lack of search also causes distribution drift. So during training time, what we aim to learn is a probability of the next reasoning step given the previous reasoning steps. But which previous reasoning steps? The one that were given in the chain of thought data. But what do we do at inference time? At inference time, we do something else. At inference time, we predict the first reasoning step, which is likely to be different from our data. And then, based on what we predicted, we predict the next one, and based on both of them, we predict the next one, and so on. So there is a difference in the distribution on which we trained and the distribution that we applied during inference. And this difference between the two distributions can cause distribution drift. So what has been proposed in the literature? To use reinforcement learning, specifically algorithms like PPO and GRPO and many, many other variants of them. The real difference, or the big difference between these algorithms and what is happening in supervised fine-tuning is that now during training, we also use our own predictions. So the model predicts a sequence of steps, gets a reward, and repeats this process many, many times. Based on the rewards, the model learns what reasoning chains are good and what reasoning chains are not good, and boosts the probability of the good ones and decrease the probability of the bad ones. And this approach has led to a revolution, led to the large reasoning model revolution. The question is, okay, so are we done? Can we now, based on reinforcement learning, take large reasoning models and build a scientist out of them? So we tried it on difficult tasks. We created a data set of challenging algorithmic problems that requires dynamic programming, graph theory, and logic in order to solve them. And what we saw is something very interesting. We saw that depending on the difficulty of the task, the model either succeed or crash. But crash means zero probability of success. So when we talk about easy problems, then the model can handle them. But there is a phase transition. When we go to really difficult problems, we see a crash in the success of a state-of-the-art algorithm like GPT-5, Gemini, Grok, and the rest. What is difficult and what is easy, and what's going on here? What is missing? Why do PPO and GRPO fail? So the reason is that these algorithms start with sampling from the base model. Now, if you sample and the probability to succeed is very, very small, then all what you sample is failures. And learning just from failures is difficult. You also need to see some successes in order to learn. So basically, we get no learning signal. We get just negative example, what doesn't work. But we don't see any examples of what works. And why? Why do we see no success at all? The reason is uncertainty. So if you remember again the examples that I showed about proving a simple mathematical lemma, there are uncertain steps. Whenever we have uncertain step, we need to try different things. And if it is many, many such steps, then the probability to succeed in sampling a good chain of reasoning chain, drops exponentially in the number of uncertainty steps. So for this simple reason, beyond a certain small amount of uncertainty, all models will collapse. Okay, so are we doomed? Can we do something about it? So the answer is yes, we can do something, but we need to do something else. So we proposed a new algorithm, which is called the diligent learner. And it is a new algorithm that efficiently learns to reason. What are the main ideas? The algorithm is quite complicated, but I will try to give the main ideas. So the first idea is using teacher forcing, but in a very different manner. We call it reverse curriculum. So the idea is very similar, like how humans are learning, is that you look at a problem, you cheat. You look a little bit about the solution. So you look at several steps of the solution, but you don't just memorize all the steps of the solution. You say, okay, I will take step 1, 2, 3, but now let me try myself step 4, okay? So now the amount of uncertainty is smaller, so we can learn it with more traditional approaches. And then after we figured out how to solve, given steps 1 to 3, how to solve step 4, we can go backward and say, okay, now let's try to solve 2 steps, and so on and so forth. So on one hand, we are using teacher forcing in order to get signal. On the other hand, we might suffer again from distribution drift because we use teacher forcing. So in order to eliminate distribution drift, we explicitly learn the model to backtrack, to understand what it knows and when we are at a dead end and we need to start over. And this is very important and, in my view, an essential part of how reasoning should be taught. You must understand when you are incorrect and you need to backtrack to the right place. Now, the third problem is maybe there is an exponential blow-up because we are going back and forth. Maybe it requires many, many steps like search algorithms. So the main difficulty is to come up with the right schedule and the right balances in order to make sure that we are not having an exponential blow-up. This is a really tricky part. And I will not explain how we do it. You can see in the paper, but I will just give the bottom line. The bottom line is what we proved is essentially a set of sufficient conditions for succeeding in learning to reason. And the 2 conditions are, first, that the basic model has some probability, non-negligible probability, to elicit a correct reasoning step. Just a single reasoning step, not the entire thing, but just one step. And this is a very reasonable assumption because today's models are very capable in learning to do just one step. And the second assumption is that if you look at the reasoning chain, then in retrospect, you understand whether you are correct or wrong, and you know if you are wrong, where to backtrack to. So where did you lost your way? And this is also a very reasonable assumption on today's models. Once you show them a complete trace and give them the signal of success or not success, figuring out what went wrong is much easier than actually giving in advance all the steps. If you think about it, it's maybe like P and NP. So NP is the ability just to validate a solution, but problems in NP, meaning that you know how to validate if a solution is correct or incorrect, but finding a right solution is much more harder. So here again, we assume that we can validate if a solution is correct or incorrect, but not that we can actually search over the space. And the theorem tells you that if you can know to validate, then you can also know how to search and succeed in polynomial time to learn how to reason. So to sum up, what we showed is that when we go beyond problems that have few steps of uncertainty to problems where there are many steps of our uncertainties, then existing large reasoning models simply fail. And they cannot solve really difficult tasks, the tasks that we want scientists to solve. And if we want to make real progress in scientific and engineering, then we must solve difficult tasks. And difficulty, we define the difficulty by the number of uncertain steps in the reasoning process. And the diligent learner is a new approach for tackling this problem with theoretical guarantees and also with reasonable assumptions, which matches what today's models are capable of. Thank you very much.